All right, we're starting a new chapter. This is chapter 10. We're going to talk about gases, the property of gases. All right, so as you begin taking your notes, it says kinetic means what? Well, kinetic means motion. Kinetic molecular theory explains the behavior of gases based on their motion, based on the motion of the molecules, and it's a theory. So we're going to take a look at some assumptions, some ideas within this theory that help us understand what the behavior of gases is. So here's our predictions or our assumptions. First one says that gas particles are tiny compared to the great distances between them. All right, so they're just kind of all alone. They can't interact with other gas particles. They're just very tiny, isolated particles. They move at random. You can't really predict if they're going to go left or right, other than the fact that they bounce off of things. They have high velocities. They move in all different directions or randomly and at many different speeds. The particles do not interact with each other or the walls of their container except during momentary collisions. So we'll think about the collisions. We'll think about the particles don't form, the particles bounce off of one another, so they don't form a compound with everything that they hit. They don't lose energy. They don't change shape. All right. So let's describe those collisions. Write this down. Collisions between gas particles are elastic. It means they conserve energy. So if they bounce off of a wall, they will bounce back with the same velocity because they have the same energy. The average kinetic energy of the gas particles is directly proportional to the temperature of the gas in kelvins. Notice how it says the average kinetic energy of all the particles. All right, that is very important when it comes to temperature. We'll talk about that later. All right, let's describe properties of gases. Let's talk about the fluidity. Gases are considered fluids because they have the ability to slide past one another and take the shape of their container. So you can pour gases and they will pour out of a container and slide past other particles, and then they'll spread out to take the shape of their new container. Gases have permeability. This is the ability of a gas to mingle with or pass through another porous substance. So picture little tiny gas molecules being released and then mingling with other gas molecules. This permeability is one of the reasons you can smell something through a piece of paper, or you can smell something maybe coming up through cement. Cement is porous. You might smell or sense gas particles coming through. All right. Compressibility. High pressures can squeeze gases into smaller volumes. So take 100 molecules all spread out, and you can take the same 100 molecules and just condense them, squeeze them into a smaller container. They have expansibility, the limitless ability of a gas to expand in an environment of lower pressure. So think of it this way: if your compressed air inside your tire is suddenly released, where do those molecules go? Well, they continue to just spread and spread and spread within the limitations of gravity pulling them down, but they continue to spread out. Diffusion. Diffusion describes the spontaneous but uniform spreading and mixing of particles caused by particle motion. For instance, if I put food dye in a glass of water and I don't mix it, eventually the entire glass of water will look the same color. It'll be diluted, but it'll be the same color as the food dye because the particles of the food dye have spread out. Gas particles behave they diffuse across the room. So the particles of aroma that you might smell from something baking, from somebody putting lotion on. Those particles of aroma spread, and if you're near the object, if you're near the source, of course it will be stronger as the molecules are more concentrated, but as the molecules spread out, the aroma would be less strong because there'll be less particles. The point is they diffuse or they spread out across an entire area, an entire room or container. Effusion is almost like diffusion, except it's when gas particles pass through a tiny opening into an evacuated chamber or space. The important part is they're passing through a tiny opening. So there is a way to measure the rate of effusion. I'm going to give you the formula, but we will not worry about using it. It's called Graham's law of effusion, and it states that the rate of effusion for a gas is inversely proportional to the square root of its molar mass. So in other words, the larger the molecule, the slower it comes out, the slower multiple of those molecules come through a tiny opening. So again, there are some practice problems on your worksheet. We're not going to worry about them. What we're going to focus on are conversions and properties, other properties of gas. So we're going to talk about pressure. Gas particles are constantly moving. Molecules have energy when they collide, so they exert a force on a surface. The average of all forces caused by billions of collisions per second equals pressure. So let's review. Gas particles move. They have energy, kinetic energy, because they're moving. Because of that energy, they exert a force. And then the average of all the forces caused by billions of collisions per second is what we sense as pressure. We can feel air pressure on our bodies from the air above us. Well, actually, you don't sense it too much, but it's there. Okay, gas pressure is the observable result of billions of molecular collisions. All right, we don't see the molecules colliding, but we know that they are there based on the pressure that we can observe. How do we measure gas pressure? We measure it in, oh, I didn't write this down. All right, the first one should say pounds per square inch. All right, PSI stands for, letter A should be pounds per square inch. Letter B, the abbreviation's there, the words aren't there. The first part is millimeters of mercury. So picture a column of mercury that's about 800 or 900 millimeters high, and as the pressure pushes down on an open container and pushes mercury up inside this glass column, you measure that height of the glass column as millimeters of mercury. Torr is just another name for millimeters of mercury. Atmospheres is just another way to count for gas pressure. Pascals. Pascals is the standard unit. We use pascals more often in physics, though. We will actually be using millimeters of mercury and atmospheres most of the time in chemistry. So what are the conversions? So one atmosphere is equal to 760 millimeters of mercury, or 760 torr. It's equal to 14.7 psi, which rounds to about 15 pounds per square inch. Think of the pressure on your hand. It equals 101,325 pascals, or the standard unit in physics would be 101.3 kilopascals. gas volume depends not only how many gas molecules are present, but also on the temperature and pressure. But we're going to stop there, and I'm going to show you a couple of simulations. This one is for diffusion, if you can see that there. Whoops. Okay. I'm just going to put, let's see here, a bunch of particles. Here we are. Blast some particles in there, make those appear. I'm going to show that the center of the mass of all these particles is right here, but as I remove this wall, the wall in between them, here we are, remove the divider, the particles slowly start to spread until the center of mass should be right in the center of this room, right where the arrow is. So they might go back and forth, it might be a little off balance, but the center of mass will start to remain in the middle. Let's take a look at this. Let's start over. What about particles mingling with one another? All right, let's remove the divider between two particles. Let's show the center of mass for each container, for each color of particles, right? The center of mass is the center of the container currently. When I remove the divider, the center of the container is now in between them. So the center of mass will slowly go towards the middle as these particles flow. They're like a fluid, and diffuse. The particles are spreading through the container. They have fluidity because they're flowing. They have permeability because they're able to slide through one another. And they're diffusing to spread out evenly throughout the entire container. All right, let's take a look at another simulation that deals with temperature and pressure, or temperature and kinetic energy, sorry. So let's take a look at this. I don't think we need the stopwatch, but let's put some particles in this container. We'll put some heavy particles and some light particles. All right, so they're all moving around. All right, now they have kinetic energy. They're bouncing off each other. Some great elastic collisions. Let's increase the temperature and watch the particles. Do they increase or decrease in speed? All right, so they're increasing in speed, increasing in kinetic energy. If I lower the temperature on the simulation, okay, we have ice cubes popping out. That is really cute. What happens to the speed? Oops, I have to hold that down. I guess I can't let it go. Yeah, it bounces to normal. If I hold that down, the particles slow down. All right, and that's the end of your tutorial for today. I hope you have a wonderful day.